At its core, an IP address is a string of exactly 32 ones and zeros. Every second, billions upon billions of packets of data navigate a massive, branching labyrinth of fiber optic cables. The volume and speed of this traffic leaves zero margin for error in how data is routed. When a data packet hits a router, that machine has to make an instant decision. It needs to identify if the destination address belongs to a massive global internet service provider or a tiny home network with only a few devices. Reading the entire 32-bit sequence just to calculate the size of the destination network takes time and computational power that busy routers cannot spare. To manage this, early network architects created IP address classes, a system that hard-coded the scale of a network directly into the address itself. Look at this sequence. Instead of scanning the entire number, the router uses a shortcut. It only reads the very first few bits on the far left of the sequence. By utilizing this initial binary sorting, early architects enabled the network to categorize data based on its destination size without ever processing the full address. Class A locks the first bit to 0, restricting the decimal range to 0 through 127. This leaves 24 bits exclusively for individual host addresses, creating room for over 16 million devices per network to provide capacity for ISPs. When an address starts with a 1, the system moves to Class B, locking the second bit to 0. This 10 prefix pushes the first octet to 128 through 191, dividing remaining bits equally between network and host addresses. Every time the system locks in a new binary prefix, it halves the available IP space to serve the next tier of organizational size. The routing system also required a third tier, designed specifically for the high volume of localized, small-scale networks. For Class C, the system locks the first 3 digits to 110, updating the decimal range to 192 through 223. Only 8 bits remain for host addresses, creating a hard limit of 254 usable addresses, fitting a small office. The last slivers of the 32-bit space are defined by the 1110 and 1111 prefixes. Class D uses 1110 to handle multicast traffic reaching groups simultaneously. Meanwhile, Class E starts with 1111 and is reserved for experimental use. By checking only these 3 or 4 leading digits, the routing system could sort every possible 32-bit address into a specific organizational category. For the early internet, the class system provided the fast, predictable routing logic needed to move data at scale. However, as the network grew, these unyielding boundaries created massive address waste. If a company needed 300 addresses, they were too large for Class C, but far too small for Class B, leaving tens of thousands of addresses assigned but unused. To fix this, CIDR, classless interdomain routing, replaced the fixed classes. The rigid boundaries were removed in favor of a fluid scale. Using a flexible /prefix notation, network sizes can be defined precisely, resizing the host space without locked binary boundaries. Even though CIDR is the standard today, Class A, B, and C terminology is still used throughout network documentation and troubleshooting. These rigid mathematical classes provided the initial structure that allowed the early internet to function until more flexible systems could be developed.